Well, I hope Mateus is going to keep me on time. That was his task. So I'm going to try the impossible, which is talk about some of Bruno's important contributions to math finance. But since I like trying possible things, sometimes if 10% works, I'm already happy enough. And let's try to get 10%. So I'm going to give you a few words about local volatility models and some of the topics that we have explored thanks to the influence of Bruno in a certain sense. So, so let me start from the very basics. I know I don't need to say these things in this audience, but the option pricing problem, as you know, is to find the fair price of an option that pays a certain value h at expiration time t, or perhaps something that depends on the path or more complicated exotic options. But this basic problem was the subject of a very important contribution by Black-Scholes method back in the 80s. And they basically found the famous Black-Scholes formula for the computation of the price of such option. It's a solution to a PDE. So PDE comes into play immediately. PDEs come into play immediately. It's a parabolic PDE with constant volatility, sigma, and it's a final value problem as stated here. The T here is T less than capital T, less than or equal to capital T. And an example of the payoff is, for example, in the case of a call option. Well, as it turns out, this simple PDE had a solution. In the case of the call, you can actually write down the solution, and everything is written down in terms of the main quantities that are interesting in this problem, namely sigma and r, and of course the parameters of the specific option. However, there are lots of assumptions here. Non-dividend paying, but that's just for simplicity. You can easily change that and get the correct thing for continuous dividend. If it's paying dividends in more complicated ways, of course, these things can get as complicated as you wish. There is the assumption that the market is complete, frictionless, blah, blah, blah. And there is the assumption that we are undergoing the exponential Brownian motion dynamics. And there is the most, let's say, severe assumption, in my opinion, which is assuming that the volatility is constant. And it turns out, of course, that this is not the case. Well, that gives you, for example, nice plots like that, very simple plots, typical solution of a call with expiration at time, with time 0 to expiration is the payoff here that you see. It's this payoff of the call, typical, and here it took the strike to be 100, and things smoothen out. Well, but nobody can actually claim in sane mind that volatility is constant. In different ways you can compute volatility. So this is, for example, the volatility of the Brazilian stock exchange, Ibovespa index, and the analyzed volatility is oscillating and is undergoing a random process. Yesterday we learned from the nice mini course from Jim Gaddero. Where is Jim? Oh, Jim, there you are. Yes, that you should model that as rough volatility. If one uses some kind of Garch model, that's what you get. And I promise that in the future I'll put also the parameters of the rough volatility for Jim's pleasure. But, so my point here is that it's not constant. So not being constant, we have to look for different models. And so this stochastic behavior of the volatility is something that has to be taken into account. And yet, I'm sorry, the Black-Scholes formula allows us to define the concept of implied volatility, which is the value of the volatility that should be used in the Black-Scholes formula so that we get the quoted market price of the derivative. So you just look at that formula, you solve the inverse problem, and this is actually my, and you get a map from sigma. You solve the direct problem here, of course, and now you want to solve the inverse problem, so you get the implied volatility given for that price, okay? Turns out that this is a monotone function, and it's one-to-one within the non-arbitrage bounds, so it's a very nice map. You can invert it. Well, so the usual phrase here, it's a wrong number that when you plug it into the wrong equation, you get the right price. So implied volatility turned out to be a crucial thing. And as you look at the implied volatility surface from the map, from the prices of the market, what you do immediately is that you see this skew, this smile curve, as people got to know it. And so that immediately shows that even at the level of modeling, there is no way the volatility can be constant, because if it were constant, then it would be you would have a flat surface there. So the question is how you match this skew, how you match this. And there have been a huge body of literature, and I'm actually talking this to an audience that many people have contributed tremendously, so you can go into these directions. I'm going to pick a few names just, so of course, I showed you I showed to you the first, the econometric vision of the volatility. Then I discussed the implied volatility. One has the stochastic volatility models, fast mean reversion, which leads to a very nice body of work, actually, theory developed by George Papanikolaou, Jean-Pierre Fouque, Sirkar, Sona, and collaborators. In the case of commodities, we have, I had the pleasure of working with Jean-Pierre and Yuri on this topic, and this was one of my, I think, happy moments in trying to go along these stochastic volatility models. One can also go into the non-parametric models. And what I mean by non-parametric is that you, in principle, well, it's non-parametric in the sense of statistics, in the sense that you are going to look for a function of the volatility of the different variables of the model, and a function of the different variables of the model, and that would be a way of giving you a description of the volatility. There are different directions that myself, I have the pleasure to work with a number of people on this. In particular, again, with Yuri and Shu Yang, we looked at stochastic volatility models. More recently, with my former student, Vinicius Albani, I have looked at local volatility. There is the rough volatility models that I already mentioned, that have been studied by a number of people. I'm citing just a few that are closer to my mind. I didn't even have time to check the full history, but I'm certain that Jim will provide you with different names. Just last week, I saw a very nice talk by Julien Guillon at FGV. It was an invited talk, right, Yuri? At the FGV about path-dependent volatility. Unfortunately, I was not able to attend till the end, but it was a very nice talk, and I'm sure that you can talk about that with Julia. So these different directions of volatility are certainly directions that have been the subject of the attention by many people, and what I'm going to do is try to discuss a few issues in the remaining time of my talk. Let's see how much more time I have. Perhaps I should stop here. Oh.
Yeah, so like 15.
Okay. And so what are the central problems? Of course, you want to understand the volatility behavior. You want to protect portfolios against volatility oscillations. You want to find parsimonious and efficient models. So this is my wish list for Bruno's birthday, or his wish list for his birthday. And you want to calibrate the models in a robust and effective way. Price order derivatives consistently and validate such models across different time scales. And there comes one of beautiful contributions by Bruno, which in a certain sense tackled some of those problems that I mentioned. So this is a copy of the first page of one of his seminal contributions. I believe this is the 94 issue of risk, but at the end, and yesterday I spent part of my afternoon reading this paper, there's a mention of the proof that is in another paper which not even in Russian sites was possible to find. I don't even want to mention the name of the site that I looked for. But anyway, so I'll try to find that. But so I'm going to give you my take of this and my motivation. And perhaps over caipirinha tonight, Bruno can tell us more about his motivation, or during his talk today, he might want to discuss that a little bit. But totally on the hinder side and completely, let's say, the moment I got completely convinced about the beauty and the importance of the model is when I looked at Jong's theorem, which tells us that if you have an Ito process, let's say 1D, just for simplicity, it actually works in more dimensions, then so as a good Ito process, you can write it as into this form where alpha and beta are suitable adapted processes. And the claim in the theorem is that there exists a Markov process, y of t, such that dy is a t yt dt plus bt dt, b of t y of t dwt. So this is the volatility part, where y, which is the one that exists, and the original x turn out to have the same marginal distributions. And furthermore, you can write b square, which is this variance part here, the quadratic variation of the process, as the expected value of the instantaneous volatility of my original process. So what you get here is basically a function of t and y. So for me, that was extremely convincing. I'm sure that Bruno had his vision of this from reality in the market. Since I was training most of my time as a mathematician, by looking at this, I said, okay, this is a good description of reality. I'm happy with that. So the assumption, the local volatility model says basically that sigma is a function of time and x. X is the underlying that we're considering. And if one assumes then that the dynamics in the risk-neutral measure is given by this form, then you have, after some elementary work, as usually, with the same tricks that you do for Black-Scholes, or the same modeling that you do for Black-Scholes, you get a partial differential equation, again of parabolic type, final value problem, where sigma turns out to be variable with respect to time and x. So, and from now on, I'm going to consider only the case of calls and puts. So being calls and puts, we have expiration time t, and we have the strike k. So in a certain sense, another miracle happens. And the next miracle that happens is that we are going now to look at the prices as functions of capital T and K. And it turns out that if we look at the prices as functions of capital T and K, then I'm fixing now the present time. I don't want to fix this present time for too long, but I fix the present time. I fix the state of my price X. And then what Bruno showed is that there is another equation, now a parabolic equation with an initial value problem where, let's say my initial time t is 0 here, otherwise I could put t here, there's no problem, such that now the u satisfies this PDE with respect to capital T and K. So it turns out now that you have an equation that is an evolution equation for the variable capital T and K. You can rethink this now as time to expiration, and you can look at your prices as a function of time to expiration. A rewording of that is that somehow there is a fictitious evolution, a stochastic process coming from expiration time equals to 0 towards u now, so as expiration times increases, such that the corresponding equation is this. Okay? And again, this is associated to stochastic process. So this is fantastic, and in the paper that I showed, there are beautiful plots, and I'm going to just mention, because I think this is a beautiful way of looking at things. So you have capital T here, and so instead of starting from t equals 0 and solving the equation, let's say, by difference or by approximation, finite difference approximations, as time goes by, you look at the payoff and you go back. Okay, and this is, I think, a very nice paradigmatic approach. And okay, and since I really wanted to do something kind of comprehensive in this beginning, especially for students, I decided I'm going to venture in providing you with one of the different proofs of this result. The reason why I want to provide you, well, it's mostly for students, so Bruno can sleep for 5 minutes if you wish, or can hate me forever for the way I'm going to describe this proof. But the reason why I want to mention this is that if you try to do it as an exercise, it turns out to be not such an easy exercise, even if you know the result now. A few years ago, when I started working on this area, I had with me two extremely strong analysts from Buenos Aires, Pablo Amster and Pablo De Napoli. These are, and we started to wonder what are the different generalizations of this. It turned out that this is extremely difficult, and generalizations of these results require lots of different assumptions, and we actually wrote one paper about this, generalizing it to basket options, but we had to make assumptions on the sigma. Then we found out there was a paper by Olivier Pironneau on the topic also. There were other papers, but the results are complicated when you try to do it for more dimensions and generalizing. So let me just give you my take of this. So let's suppose R and D are both equal to 0, and therefore you're working with dx equals sigma x dw. Well, that leads to a probability transition from t to capital T, x to psi, and the corresponding Fokker-Planck equation for such probability is this one, just a standard stochastic calculus. Then with that probability transition, you can actually write down the call price, and the call price is integral from k to infinity of psi minus kp the transition function. By the way, I've seen this proof in many books. This is very much in the spirit of what's in Jim Gatherer's book. Although I'm an extremely detailed analyst and I want to put all the variables, I think this is easier to follow. Perhaps not. So this is basically the proof that you can find, for example, in Jim's book. And now if you differentiate this, of course, under the reasonable assumptions on sigma, bounded from below, blah, blah, blah. And then you can put the derivative here inside. And now you use the Fokker-Planck equation. And it turns out that after integrating twice, you get this probability transition function, integrating once by parts and the other one just using fundamental theorem of calculus. Now you call in a result by Briden and Litzenberg that, or basically an exercise in differentiation, but this result turns out to be very important, by the way, is that the probability density that I just wrote here is the second derivative with respect to k of u. And there it goes. So there you have the Dupire's equation. By the way, and there are some points that have to be made here. If you try to do this in more dimensions, it's much more complicated. Even to find what's the right generalization is a tough thing. There is work by Amel Bentata on this, and that's one of the, for the case of jump diffusions, and it goes, it's deep work. It's not a trivial thing. The other remark is, if you look at the case, the original case that I had R here, and in principle you could have dividends, blah, blah, blah. It's just a question of rewriting these using a few properties, and basically you get that. There is a nice comment on Bruno's paper about this, and this immediately allows you to compute sigma as a function of the prices. So, in fact, if you look back into the general case, what happens is that you get a way of fitting your smile curve from the volatility that you are having in the model. So if you choose sigma such as this, then you can fit the smile curve. However, there are problems in practice to estimate sigma from here. With limited amount of discrete data, we need to interpolate, or we need to do some kind of a priori information, and that leads immediately to a very, very problematic thing. And in fact, you get numerical stabilities, and even to keep this argument positive is hard. So that leads us to look into how to handle such difficulties. And the focus of the rest of this talk, how much time I have? 5 minutes, oh my God, is to, well, I have time to put my take-home message and perhaps. So the focus is Dupire's local volatility models, and the goal, at least, of this sermon, this lecture, is to mention that this is an ill-posed inverse problem. And it's ill-posed in a very technical and clear sense, trying to get the sigma from just a few data points, no matter what you do, no matter if you believe in ensemble something, you are going to have to handle such problem. It's a fact of life. You have here u, you don't have u with full information, you have to take second derivatives, you put whatever spaces you want, you put, and unless you assume that you have control of the second derivative in a correct H2 norm, you are stuck, okay? The other point is the sparsity of the data is extremely important. And what we did for many years is try to use convex regularization techniques, which are actually results that have been worked. And many of these results are in the context of Banach spaces. They are deep results. They are not just standard theory, as some people might have thought. I've even seen such comments made in referee reports and things like that. It's not the case. And if anyone wants to know, I can show you. And we got convergence results that include convergence rates and noise level in different contexts. And we go way beyond classical quadratic regularization. So now what are the applications of this? Risk management, hedging, evaluation of exotic derivatives. Inverse problem theory is, in a certain sense, the way people handle such problems. And so we have parameters, we have a forward model. In this case, the forward model turns out to be Dupire's forward equation or some version of it. We have noise data. We want to go back to the parameters, and from that, we want to compute the quantities of interest. To show you how much this theory has been developed, and this, of course, has not been developed by me, whenever you go to take a CAT scan and you get pictures such as this, you get a tremendous amount of theory behind it. People debated throughout the 60s on the different artifacts and the different technical issues behind getting such pictures with precision. And this is an example of linear problem. Turns out that there is a lot of functional analysis behind it, numerical analysis, computing, and so on. So to throw that away just by saying, okay, I have a direct method of solving the problem, I think it's not really the way to go. Although direct methods might be important. And a few years ago, I was very happy to be with a group of Berkeley people, and we actually got a paper on the nonlinear case. And this problem, as far as we know, is still under work by many people, by many groups. To show to you how many people in the volatility context have worked, I have made a small list. This list is as of 5 years ago, so there is not mentioned to a number of people. Some of those are here, but I'd like to mention in the case of the approach by Crépé, Stéphane Crépé. Is Stéphane here? Oh, Stéphane is not here. Okay. Okay, that's a way of, yeah. And that's actually one of the, I think, most relevant contributions to looking at this problem from the point of view of inverse problems theory. So in the remaining of this talk, I just want to mention that we then go through Dupire's equation. We massage the equation a little bit. We look at an initial condition now, we just of this form, and now we have a nice PDE. By the way, this PDE, if we didn't have the minus here, we would have the traditional heat equation with traditional diffusion properties. And I was very fortunate a few years ago to have a collaboration with Ottmar Scherzer from Vienna. And it turns out that the cone conditions that allow us to prove convergence of the inverse techniques don't hold if you didn't have this minus here. So this shows that we are talking about something special, just the fact that we have the minus here. Anyway, we set up the calibration problem. We produce a parameter to solution operator, and we attack the problem from the point of view of inverse problems. In particular, the fact that we have this parameter to solution map satisfying these two conditions, which I'm not going to mention, has a technical consequence that the inverse problem is ill-posed, and one has to actually use regularization theory to actually solve this problem. Reminding you that well-posedness means that one of these three conditions are satisfied if it's ill-posed at least one of those. In our case, the stability is the main issue, and that's the main problem here. So we use convex regularization with different functionals, and we have then analyzed this under some assumptions. So, for example, there are technical theoretical questions that have to be answered immediately. For example, does there exist a minimizer to the regularized problem? The answer is yes. How to choose the regularization parameter here in a proper way, that we find a way of doing that. And suppose now that the noise level goes to zero. In other words, suppose that the uncertainty that I have about my data goes to zero. How fast does the regularized solution go to the true solution? We get the convergence rates. This was published a few years ago in the paper with Schatzer. And we also get iteration techniques, iterative methods to solve the problem. We have developed different techniques to attack this. And we have proved convergence of the iterative method. Okay? So I think in the interest of time, what I'm going to do is respect the imponent presence of our chairman, and I'd like to stop here, but I just want to go to the final. But no. At least I have to do one punchline. Say, happy birthday, Bruno, and one of the different pictures that I covered, this was Rio 2011 back in Angra a few years ago, and Bruno is hidden here, concentrated, a new approach to volatility derivatives. So thank you very much for your seminal contributions.